Just got your message about joining early, so sorry it wasn't early.
All good, all good. Awesome. So I think we will just want to wait a minute or two to see if anybody else rolls in. How's your day been?
Good. It's a beautiful day out, so it's been nice.
Nice.
And then
Awesome.
I'll be able to like share my screen, right?
Yeah, you can share the screen.
Okay.
Yeah. Cool. Let's just get started with it. So welcome everyone to the Davis Engineering Team Workshop Q&A. Our questions and answer with Aadeel Akhtar. So make sure that you are joining the remind by texting at Team Davis to the number that you see above, and that way you can get caught up on announcements and current events for Davis Engineering Team. And here I'll just go through like what we'll be doing. Can you switch the slide? Yeah, so basically we'll have Aadeel will give a quick introduction about himself and his career, and then we will have most of the time just dedicated to a Q&A discussion on just with Aadeel, and then we will close out the workshop. So yeah, Aadeel, if you want to start the introduction, you can go ahead.
Cool. Here, let me get the screen sharing started. Here, let's see. We'll do entire screen. Okay. All right, do you guys see my screen?
Yeah.
All right, great. So yeah, thanks for having me, guys. So my name is Aadeel Akhtar. I'm the CEO and founder of PSYONIC, and we develop advanced bionic limbs that are affordable and accessible for everyone. For me, this started out as something I've wanted to do ever since I was 7 years old. My parents are from Pakistan, and I was born in the Chicago suburbs, but I was visiting Pakistan, and that was the first time I met someone with a limb difference, and she was my age, missing her right leg, using a tree branch as a crutch, and living in poverty. And that's what inspired me to want to go into this field and develop advanced bionic limbs that were affordable and accessible. And so I went to Loyola University of Chicago for undergrad, and I was pre-med and a biology major. And the goal was to become an MD who works with patients with amputations to make devices for them. And it wasn't until my sophomore year of undergrad that I took my first computer science class, and I absolutely loved it. I loved everything about coding and engineering and programming, and I realized that if I became a straight-up MD, I wouldn't get to do any of the cool stuff that I learned in my computer science classes, and I wanted to figure out a way to combine that. So right down the street at a hospital called the Rehabilitation Institute of Chicago, it's now known as the Shirley Ryan Ability Lab. It's the #1 rehabilitation hospital in the US for the last 31 years. And they made huge breakthroughs in mind-controlled bionic limbs. And it was the perfect combination of like computer science and engineering and physical medicine, rehabilitation and neurology. And it was exactly what I wanted to do. Except that, you know, the hands that they were using were like $100,000 to make, and they were super fragile. And so that spurred me to want to start developing our own devices. And so I ended up finishing my bachelor's in biology at Loyola. I got a minor in computer science and a minor in neuroscience. I went on to get a master's in computer science from Loyola and taught in their CS department for a couple of years before going down to the University of Illinois at Urbana-Champaign in 2010 to start the MD PhD program there. And I ended up getting another master's in electrical and computer engineering, and then a PhD in neuroscience. And technically, I'm on a leave of absence from medical school right now, but honestly, this is way more fun, so I don't know if I'm going to go back. But while I was while I was doing graduate school, we got the chance in 2014 to go down to Ecuador and work with a nonprofit organization called the Range of Motion Project there. And their whole mission is to provide prosthetics to those who can't afford them in developing nations. And so we had they were able to sponsor me and another graduate student through the U.S. Embassy to go down there and try out one of our like super early 3D printed hand prototypes on a patient there, Juan Suquillo, who lost his left hand 35 years prior due to machine gun fire from a helicopter. It was a border war between Ecuador and Peru, and he was able to control our hand and make a pinch with his left hand for the first time in 35 years. And this next video I'm going to show you kind of captured, that was one of the international news stations that captured that event of that day.
Un quiteño es el primer beneficiado de una prótesis de mano con ayuda en su financiamiento. El programa es realizado por jóvenes de la Universidad de Illinois en Estados
That's so
Unidos.
awesome.
Juan Suquillo es excomandante de guerra. Fue así como perdió parte de su brazo. De esto han pasado más de 30 años.
Varios miembros de mi pelotón sufrieron heridas y particularmente la mía me cobró el brazo izquierdo.
Gracias al avance de la tecnología, hoy puede acceder a una prótesis.
Parte de mí ha vuelto.
Jóvenes ingeniosos y
My hair was cooler
para
then.
ayudar al próximo más necesitado han desarrollado una prótesis de brazo bioeléctrico con la posibilidad de retroalimentación sensorial, es decir, sentir como una mano de verdad.
All right, so a couple things I want to point out, right? First, that, you know, this hand is like 3 times the size of an average adult human hand, had wires going everywhere, plugging into breadboards, plugging into power supplies, plugging in the wall, right? You name it. Despite that, Juan said in front of these international news stations that he felt as though a part of him had come back. And that was because he made a pinch with his left hand for the first time in 35 years. In fact, he had forgotten how to make a pinch, and we had to retrain his brain by placing a mirror in front of his amputated side, reflecting his sound right hand, and tricking his brain into thinking that his left hand was there, so that when he made a pinch with both hands at the same time, it reactivated those muscles on his residual left limb. And that way he was able to actually make a pinch with our hand using the machine learning algorithms that are on there. And so when he said that, you know, a part of him would come back, that's when I realized that if we stay in like academics, like if I become a university professor or go like the traditional MD PhD route, then this just stays a university project or a journal paper, and that's the end of it. If we want everyone to feel the exact same way that Juan did, we had to commercialize the technology. And so that's when PSYONIC was born. And so we went back to, you know, the University of Illinois. We won our school's business plan competition. We won the Illinois Innovation Prize the next year. We won several grants from the National Science Foundation and raised a pre-seed round. And then as of September of last year, the Ability Hand is now available nationwide. It's FDA registered and covered by Medicare. And so that's what it looked like back in 2014, and this is what it looks like now. And so this is retired U.S. Army Sergeant Garrett Anderson doing push-ups for the first time since his Army days. He's holding like a 40 to 50-pound kettlebell, and he's able to easily, do kettlebell swings with it and lifts with it. You can do all sorts of activities of daily living. So this is one of our patients closing his laptop lid. One of our patients in Chicago, she was able to feed her granddaughter for the first time. By holding her granddaughter with her intact left hand, and then feeding her with her bionic right hand. And it's just made a huge quality or a difference in the quality of life for our users, in having them able to do these activities of daily living much more easily than they would with just one hand. And so this is an overview of the hand itself, and I'll kill my screen really quickly so that you guys can see the hand in real life right over here. So I've got it with me right over here. So the way you control it, let's say you're missing your hand right below your elbow. The most typical way is that you'd place muscle sensors, so over your wrist flexor and over your wrist extensor, right? So those muscles are located in your forearm, right? So right over here and right over here. And these two buttons on here, they're basically emulating what those muscle sensors do. So if I close it, you can see all 5 fingers flex and extend on the hand, and the thumb rotates as well. And then if I open it twice, I can actually switch it to a different grip. So this is what we call a key grip. So if you're holding like a key or a credit card, or if you want to give someone like a thumbs up, I can slide that over, and then it turns into a power grip. So I'd be able to like hold a mug or a kettlebell like you saw. This is the fastest bionic hand in the world. The fingers close in 200 milliseconds, which is actually faster than we blink our own eyes. We blink our eyes in on average 300 milliseconds. And if you flex your muscles lightly, you can actually control the speed that the fingers move at. So here's the hand moving much more slowly. So if you want more precision, then you can do that too, but you can also make it move very quickly. So when the hand is open, I open it again, I can switch to the next grip. So if you want even more precision, here's like a pinch, for example. So I can grab things like off my desk. So here, let me see if I can grab something right over here. All right, so here's a pencil that I just grabbed with the pinch right over there, and then I can just drop it right over there. So, and then, if you're at a rock concert, you can also like rock on, right? So you can do all sorts of gestures. There's Bluetooth in here, so we've got an app for it. There's an app for everything these days. But it's available on iOS and Android. Actually, you guys can all download and install it if you wanted to as well. And there's like a demo mode, so you can see all the different features that you can do with the hand. But some things about that is that there's 19 pre-programmed grips, so you can select which grips that you want to do. So, for example, you could flip someone off if you wanted to. It's something that every patient usually asks, like the first thing. But like there's other grips like a tripod grip or like hang loose and like a bunch of other ones that users can select between. It's also the first hand to give users touch feedback. So if I touch the index finger, the pinky, and then the thumb, you'll feel a vibration here, and then it'll vibrate when you contact an object, and then when you let go of the object, and depending on how hard you pressed on it, that's how strong that vibration will actually feel. And so we've got one on the a touch sensor on the fingertip, the finger pad, 2 on the lateral side and 2 on the medial side of the finger. And then for users, we've had like one of our patients is a triple amputee who lost his legs and his left hand due to sepsis when he was like 85. And he was able to grasp a hollow eggshell while blindfolded without cracking it because of the touch feedback that's available in the hands. The fingers are super flexible. So like your own fingers, they're resistant to like impact. So I can like smash this and it's totally fine. Like you saw us do push-ups on it. We've done other things like break boards with it, martial arts style. I've arm wrestled against it and lost. We threw it in a dryer for like 10 minutes and it was totally fine being in a dryer. Can't say the same for the dryer, but the hand definitely won that fight. It's water resistant up to the wrist. So we tell our users to just go wash it like they would their natural hand. We're working on a version of the wrist that's also waterproof. This is actual carbon fiber that's on here, so it's super light, super strong, so it can pop the hand off just like that. This is the hand itself. It weighs about 490 grams to 500 grams, and to put that in context, an average adult human hand weighs around 520 grams, so this is actually lighter than an average adult human hand. There's 2 sizes. This is the 50th percentile adult female sized, and then we've got a 50th percentile adult male size, which is our small and our large. And then you charge it just by using this USB-C charger right over here. So the same way you plug in your phone, you can plug in your hand, and it'll charge from 0 to 100% in 60 minutes. You can use like one of those portable power packs that you use to charge your phone to charge the arm too. It usually lasts around 8 to 10 hours of battery life if you're on 2 cells, but then we can like double up the cells or triple them up, and you get 16 to 24 hours on it. You can also charge your phone from your arm too, so superhuman ability that we like to give our users. And I'm gonna try and show you guys one more thing. This is through the app. This is like an Easter egg that we've got, but there's like an invisible button on the demo screen of the app, and then if you trigger it right, you can actually get the hand to play music. So I don't know how well you guys can hear that, but
Oh yeah, I hear it. Yeah.
So this is the theme song to Doom, but basically we're using the motors as voice coils, so we can basically play any 8-bit song that you want just through the motors that we've got on here. So yeah, we have a lot of fun with the hand itself. So let me share my screen again so you guys can see some more videos of the hand in action. And here, let's see, we'll do this one. And then I'll swap those two. All right, do you guys see my screen again?
It hasn't appeared for me. Do you guys see it?
Yeah, I don't see it either.
You don't
Okay,
see
well,
it. Oh, it's good? Okay, great.
Yeah.
Great. Okay. So yeah, so this was the hand itself, right? We talked about all this stuff. The best part is that it's covered under Medicare in the US. And to get that, or to put that in perspective, fully multi-articulated hands like ours were usually only covered by the military, or if you had a workplace accident, which was about 10% of the market. And by getting it covered under Medicare, we've expanded that access to now 75% of the market can afford an ability hand. And so that was huge for us. And so here's some more videos of our users. This is 13-year-old Alex Ojeda, who was born without her left hand, controlling a bionic hand for the very first time. And you can see that she was very moved by it, and we were very moved by her ability to control the hand too.
That is so.
And so this
wait,
next video,
question.
this is one of our users 3 minutes after he was first fitted with the ability hand. Someone threw him a water bottle, and he was able to catch it because of the reaction speed.
Are you ready? It's it right here.
Oh yeah, I've seen this video.
And then just to show you guys how strong these fingers are, in this next video, on the right side, you're going to see like a traditional pin joint finger design versus on the left side, which is our compliant finger design. And we have this like giant hammer that basically falls on the finger through an impact testing machine. And you'll see what happens to the traditional pin joint versus our finger. You'll see on the right side, the finger just completely broke off entirely. And then on the left side, the finger just returns back to its original position. And then this is me arm wrestling against the para-triathlete national champion and unfortunately losing. So I'll have to get my revenge sometime and start bulking up a little bit more. But I don't know. He's a little bit scary because he can also break boards. So that's him breaking boards martial arts style with the bionic hand. And then if you guys remember that that viral trend from several years back about doing bottle flips with a partially filled water bottle, you can imagine that's harder to do with a bionic hand. And so one of our users, Kate Kettlehone, she's now a pre-med student at Johns Hopkins. She came to the lab and she just started doing, we had her do bottle flip tricks all over the lab with her bionic hand. And this next video shows a bunch of them. Let's see.
How long ago was that?
How long ago?
Yeah.
This was maybe in I think it was like September or October that we did a bunch of these.
Oh, okay. Is that just all over the university lab? Or
yep.
Is it...
Yeah.
Wait, does PSYONIC have like a headquarters, or do you guys just work out of a lab? And
Hold on. Yeah, sorry, what were you asking?
Yeah, if you guys have like a headquarters or like somewhere that you guys for in terms of PSYONIC, or do you guys just work out of a lab out of a university?
So we are in our university's incubator space, the University of Illinois'
Okay.
incubator space currently. But that being said, we're probably going to be moving in August to most likely San Diego at this point, but we're also evaluating whether Chicago is a good place for us to move as well. But things are leaning currently towards a move towards San Diego right now. And then, but yeah, so the video that you just saw, this is all in the university's incubator space. And the next one is too. The next one shows, this was one that we did for Halloween, where the hand walking on its own.
Oh, it's like fast.
And then it multiplied and became 6 hands that started chasing me. And then just because we can, this is a video of Sergeant Anderson doing 360 degrees of wrist rotation just by using his muscles. So we made him superhuman. And just to give you guys a glimpse into the future too, so we're actually agnostic to the control system, meaning that it doesn't have to just be your muscles. It could be anything that you want. It could be like brain implants. It could be peripheral nerve implants. It could be your webcam. And so this next video that I'll show you, this was a demo that we had put together for the Consumer Electronics Show, and we actually won a Best of CES award when we were out there. But it's doing real-time individual finger control just by using my webcam.
There you go.
Oh, you guys went to CES last year?
Yep. Yeah, so this was in Vegas. But you can see in that one, it's not just pre-programmed grips, it's actual individual finger control. And so a lot of these videos, they're part of a documentary that was done by Legendary Pictures. So that's the same Hollywood studio that made like Dark Knight and Jurassic World. And it's the documentary is called Make It Work, The Launch. It's available on Roku and on YouTube as well. And I can send you guys a link to it if you're interested. And this is our contact info as well. So if you want to send us an email, you can send it to info@psionic.io. It comes to me. And our director of operations as well. And so, yeah, okay. So now those are all the slides I had. So I'd be happy to take any questions that you guys have.
Yeah, definitely. I'll get it started. So first of all, like, do you, reflecting back to when you were 7 years old, how do you feel in terms of when you first initially got the goal of finding a solution to the girl that you met that had a missing limb? Like, how do you feel in terms of that? Do you feel that you've kind of honored her in a way, or maybe reached a point where, like, if she had this, then she would be had better quality of life?
So not yet, because she was missing her leg and we made a hand, right? So we do have a 5-year goal that we want to make an ability leg in addition to an ability hand that you can do a triathlon in. And that we also want to get to be able to be covered by Medicare in the US. So that once we hit that point, then I feel like then we can start tackling, like, legs in the developing nation, in the developing world as well, in India and Pakistan and Ecuador and Guatemala and all these places around the world. So there's still a lot left to do, and that's kind of what's exciting about this field, is that there's so much extra. Like, there's still so much left to do. So it's an exciting time to be working on it.
Definitely.
Yeah, I have a question. So how feasible do you think like mass producing these are, and like spreading them to more developed countries? Because I heard that was kind of your plan, and also, like, I just want to know, is it like, does it take a lot of manpower to create a single one, or can they be like easily mass produced?
Yeah, so our biggest challenge right now is that we've got more demand than we can produce, which is a good problem to have. And so we are able to make around, I think, like 4 hands a week currently. And just to put things in context, like last summer, it was about like 1 hand every 3 weeks. And it was primarily one of the reasons that's just been like stunting our just like expansion is just the chip shortage. And so there's a global chip shortage across the entire world. And we had to end up like redesigning all of our electronics to use new chips, and so we're in the process of like validating that and making that all work. So we hope to by next year start making like thousands of these, and so we can get them out to as many people as possible.
That's awesome. Yeah. Do you, what's your manufacturing process right now? Like how are you guys going about manufacturing these?
So we make basically everything in-house in the US right now. So in our offices here in Champaign, so we do all the carbon fiber molding, all the silicone molding, all the hand assembly, all like the electrical work inside, all the fabric work itself too. So that's, yeah. So basically it was the first made in USA hand available on the market.
Yeah, I have a question. So, like, if you do make these mass-produced, I'm just wondering, like, with, I don't know, like a patient that's a 13-year-old girl or versus like a 45-year-old man, wouldn't there be like a big difference in like the width of their limb that they still have, like that the prosthetic will be attached to, and like the length of their arm? So like I'm just wondering how you would be able to make this like work for all different types of patients.
Okay, so just to clarify, what we make is the hand itself, right? And then the electronics that go into the socket. A clinician will actually customize that socket to the individual user. So we can mass produce these guys, and then the clinician can custom tailor it to every single individual, and then just take our hand and then use this same industry standard connector to just like pop our hand onto it. And then they place our electronics around the residual limb of the user. And so we have several users who are above elbow amputees or like shoulder disarticulated patients. And for them, it's the same thing, right? We make the hand and then it plugs into this like industry standard connector. And there are other companies that make like electric elbows, for example. And then our hand is compatible with those elbows, and they're able to control the elbow and our hand.
I have a question. Can you go over like the basics of how it works? Maybe not like the super technical aspects of it, but just like the basics.
Yeah. So, and I think I was mentioning this a little bit earlier. So if you are missing your hand here, you place those 2 muscle sensors. Like, so there'd be one placed over your wrist flexor, one placed over your wrist extensor. And depending on
those muscle sensors, are they just reading like electrical signals? I don't know how that works. Like, how does the muscle sensors work?
Yeah, so you guys are all probably familiar with like EKG. It's like those sensors you place over your heart. You've probably seen them in like TV shows where like you go into an ambulance and then you see that heart monitor and it goes beep, 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 right? And then if you die, then it flatlines and goes beep, right? So what that's actually picking up is like your cardiac muscle, right? It's amplifying like the neural signals that are causing your heart to contract. And so imagine those same sensors, but instead of placing them over your heart, you place them over your muscles. And so when you don't have any activity and you're just relaxing your muscles, you'll see a flat line of like electrical activity. And then when you flex your muscles, it's amplifying those the voltages that are coming from your nerves. And then that's what you'll see this huge burst of electrical activity. And then we can use that. We call it an electromyographic signal, or EMG, instead of EKG, which is electrocardiograph, right? And so we can use those EMG sensors then to control the movement of the hand. So if you place one EMG sensor over your wrist flexor, then when you flex your wrist, you can actually cause the hand to close. And then when you place one over your wrist extensor, then you can extend your wrist, and that'll cause the hand to open back up. So that's just one way to control it, though. That's the most common way. But you could also use like a series of like 8 electrodes that go all around your forearm, and then a machine learning algorithm that can detect when you're making a pinch versus making a fist versus making a tripod grip. And then different muscle groups are firing in your residual limb. And if you have enough sensors, then you can pick up on all those different muscle activities and then have the hand do the same thing. So like after you learn the pattern, oh, this is what the muscle patterns look for, like a pinch or like a fist, then you can train this machine learning algorithm, and then like after like 2 minutes of training, the machine learning algorithm will like look at the muscle signals and then be like, oh, this muscle signal looks like when you're trying to make a fist, so we're going to make the hand do the same thing. Or these muscle signals look like when the hand was trying to make a pinch, so we're going to make the hand do the same thing that way. And so that's another way to control it. And then of course, like one of the things I'd mentioned were brain implants and spinal cord implants, peripheral nerve implants. And with those, it's the same principle, right? You place an electrode over your nerve. When your body tries to make a movement, those nerves are firing, the electrodes pick up the electrical activity, and we can send that to the hand and make it do different movements.
Wait, so then does that mean that like, if in terms of getting like the like data from like the muscle sensors, does that mean that every like pinch function will be the exact same movement like mechanically, or will it be like slightly different if your muscles go like a little bit to like the left or something like that? Like how's the variability in that sort of sensing?
Yeah. So when you have those two EMG sensors, as well as the we have the two EMG sensors as well as the pattern recognition, the machine learning signals. Those are sending a command to the hand that says move to a pre-programmed grip. So in that case, the pinch will be exactly the same every single time, right?
Yeah.
But with the brain implants and the peripheral nerve implants, that one is saying like, no, drive your fingers to a particular position, right, based on like what your nerve signals are reading. So when you saw that webcam demo I did at CES, that was similar to what we're going to be doing with the brain implants and the peripheral nerve implants, where I was just moving like an individual finger and it was tracking the movement, and then the hand was moving an individual finger as well. And so in that case, there's no pre-programmed grips at all, right? The hand is moving according to how you would be moving your own natural hand.
That makes sense. Yeah.
Yeah, so for training the machine learning algorithm, would you like put electrodes in someone with like a natural limb? Because wouldn't it be kind of hard to do it based on like someone with like an already missing limb? Because like they have to like retrain themselves to like make those certain movements, right? Like where would you get the I don't really know how to articulate this, but like the parent case of like each of the limb movements.
Sorry. Could you re-explain that again?
Yeah, sorry, I'm not really sure how to articulate this, but you said that you basically you map a set of signals to like an individual movement, right?
Yep.
So where do you get the first set of mappings? Like, did you just put electrodes in someone with the natural limbs arm, or did you?
Are you talking about like the implanted electrodes, or are you talking about with? So for that, the idea would be that, let's say you're missing like one hand, for example, then you'd get implanted, and then like using our like webcam interface, for example, you could put both arms up to the screen and then try and do like bilateral movements, right? So it's like your right hand, which is still there, versus my left hand, which isn't there. We're recording the nerve data, but you're trying to do both of these at the same time. So we can grab the joint angles from this side to know what the nerve data from this side was actually trying to do.
So you basically just take advantage of like the symmetry of like someone's arms.
Yep.
Like, yeah.
Yep. Exactly.
What exactly is the machine learning algorithm running on? Is it on the hand itself? Because I assume that would be, and like where would that be located?
That is the goal, is to have it running all on board on the hand. So we've got like an STM32 like ARM Cortex like M4 processor on here, and we would be running the machine learning algorithms on that.
Yeah, on your website it says like over-the-air uploading. Does the STM32 have Bluetooth on it like ESP32 would, or do you have like own Bluetooth chip or something like that?
So we use an NRF52 for our Bluetooth chip. So in the hand itself, we've got actually 7 microcontrollers. So one for each one of the motors. So there's 6 brushless DC motors in here that control each of the fingers. And then each one has its own dedicated STM32 to allow you to do like torque control, position control, and velocity control over each one of those motors. And then we have a 7th microcontroller, which is the NRF52 chip. It's also an ARM Cortex. I think that's also an M4. And then that is what does the Bluetooth communication with like the phone and the computer and whatnot. And so that also what do you call, coordinates all the different grips. So it tells like what the other motor controllers, the other STM32s, what they should be doing, essentially.
I have a question on like the mechanical aspect of the fingers. So you mentioned how the fingers move based on a 4-bar mechanism. How are they powered? How is that mechanism powered?
So we've got a brushless DC motor, a planetary gearbox, and a worm gear right over here. And so
You said a worm gear?
A worm gear, yeah, like WORM, worm gear. Yep. And so that basically translates the motion from going from rotary, like the axially, to like a 90-degree twist. So that allows
I
us
see.
to, yeah.
Yeah.
And the other advantage of the worm gear is that it's something that we call non-back drivable. So what that means is that, so when I move the fingers this way, it can't, like, you can't move the motors backwards. It locks it in place. So if you're holding like a 50-pound kettlebell, then the fingers won't, what we call back drive, they won't open back up because the worm gears are holding them in place. And that way we can like hold very heavy objects without like having to inject power into the motors in order to keep it there. So it like extends your battery life like way, way, way longer.
So the rigidity isn't depending on the motor's like components or the internal components of the motor. It's depending on the actual like metal of the worm gear.
Yep, exactly.
Okay. How is like how does maintenance relate to this? Like how often does maintenance need to be done, and like how would you even do that if that needs to be done?
Yeah, so it depends on the user, right? I mean, if you're a light user at home, then it's probably going to be a lot less maintenance than someone who's like out in the farms, like working out in the fields, right? And let's say that you take a chainsaw and you accidentally cut off a finger with a chainsaw, right?
Yeah.
So we've got 3 screws that you can take out. So one at this joint right over here, and 2 at the base of the finger as well. And then you disconnect the pressure sensor, and the entire finger can come off, and you can just replace that itself. If something goes wrong in the hand, in the palm itself, then we have to send out like a replacement hand, or they ship it back to us, and we have to fix it. But we usually overnight like a loaner hand to the user or to the clinician, and then they that way the user can continue using a hand while we fix the other one.
That makes sense. Yeah.
How exactly does the like touch feedback sense work? Like if you touch something, how would you feel it? How does that go back to the nerve?
Yeah, so like the control system, we're actually agnostic to how the user gets the touch feedback as well. So we can stream all 30 touch sensors over. So we can sensorize all the fingers. There's 6 touch sensors in each finger. So it's 5 times 6 is 30, right? So we can stream all of it over Bluetooth. We can stream it all over like a USB connection or whatnot, right? And so the way we do it clinically right now is that we've got a vibration motor. So they'll feel a vibration on their skin. So when you touch the finger, they'll feel a quick vibration for like half a second. Then when you let go, they'll feel another vibration for like half a second. And depending on how hard you made that initial press or release, the vibration will be stronger dependent on that. Now that being said, with the nerve implants, you can actually stimulate your nerves directly. And what we can do there is that when you touch here, we can stimulate your nerve and make it feel like it's actually coming from your hand that's not there. So on like your fingertip, for example. So that's like, an active area of research that we're looking into is like, how can we like make it always feel like a light touch, strong touch, pressure, vibration, pain, etc.
So I guess you could say that your main, or like the best version of this would be partnered with like Neuralink or something.
Neuralink or honestly probably even better / easier than that would be what do you call it? Peripheral nerve implants, because that way it's already the fidelity of the signal is much better in the peripheral nerves, because like it's your spinal cord has already filtered all that information out, and it's basically the signal that you were going to be sending to your skin or getting from your skin or to your muscles anyway. So that's probably like the best bet here is to do a peripheral nerve implant. But that being said, we do have partners at University of Chicago who are doing cortical implants in the brain as well. And we're in very early talks with like Neuralink as well about getting our hand controlled from their implants.
That's awesome.
All right. Going back to like education, like when you finish your major in like biology and computer science, like was the creation of Psionic the main reason that you decided to pursue like electrical engineering and neuroscience?
Yeah, so I knew I wanted to build bionic limbs all along. I just didn't necessarily know what the best path to get there was, and so originally I thought an MD PhD would be the best path for me, but then I ended up instead getting a PhD in neuroscience and a business instead of like a PhD in electrical engineering and a medical degree. So you never know where life is going to take you with this kind of stuff, and honestly, what was even more critical than like the education path was just doing the stuff outside of the classroom, like actually building stuff. We started with Arduinos. We started with like we used like a Teensy, which is basically an Arduino programmable board that's like super small. And then we kept like going from there, then to like from Teensy to an STM32 to like 7 STM32s, and then like but when we started building these hands, that wasn't part of like my research. It eventually became part of my research, but it was more so that that's what I wanted to do. So we started just like 3D printing our own hands, and it was basically like I said, outside of the classroom. We got a bunch of undergraduate students to work with us, and like who learned how to do like PCB design and like learn how to like do surface mount soldering and embedded systems coding, and then mechanical engineers who were doing 3D printing and CAD and things like that. And so we just kept iterating, and like this is the ninth version of the Ability Hand probably in the last 8 years. So, and each version was basically like starting over from scratch. So yeah.
All right, I have another question. So obviously, like in terms of so obviously Psionic is in the biotech sort of medical industry. How hard, obviously that's a kind of vague word, but how hard is the process behind getting like FDA approvals and all those different like logistics that you have to pass through just before you get something to market?
Yeah, so our hand is considered a FDA Class 1 exempt device. So we just had to register it with the FDA, meaning that we had to go on their website and then like announce that this is available on the market. And then they had like a couple regulations that we had to do. Like we had to make sure everything was labeled properly, and we had to make sure that like we have like a complaint file history. So like we were just tracking like any issues that occur with the hand. But that was it. That's all we had to go through. So that was for us, that reduced a lot of the barriers to entry to get a hand on the market in particular. Now some of the future stuff that we're doing is like with like bone integration and like muscle integration. Yeah. That's going to be like a Class 2 or Class 3 like FDA medical device. And so for that, we're going to have to go through clinical trials and like and all of that. But that stuff is even more exciting because then it's like it's powered by your own body, right? Which is the ultimate like seamless mixture of like humans and machines, right? And that's the future that we're heading towards with all this stuff.
Yeah. I have another quick question. How what was the hardest part about getting funding for Psionic, like its initial capital?
Yeah. So I mean, the first time you raise money is always the hardest. That's what they tell you. So I'm hoping that's true. But we did our first raise through just angel investors in like the Midwest and some in the Bay Area as well. And the most important thing for me was that I wanted to make sure that the investors that we had were on board with our mission, which was to make bionic limbs accessible to all people. And so it's not just all about like profit, but also the impact that it has on the individual. Yeah. And so, in a lot of senses, it's harder to find people to raise money that way, right? This isn't software. Yeah. Right? This is a medical device that is meant to help people with missing limbs. So So it was definitely like a challenge, especially also because my background is like engineering and medicine, right? So I had to like learn an entirely new language, essentially, of like like value propositions and business models and like customer discovery and like a return on investment and all of this stuff, right? Like financial projections and all of that stuff. So fortunately, we like the University of Illinois has like a great program for they call it the Technology Entrepreneurship Center, which is basically how you translate like engineering, like technology over to a business side of things. And so I learned a lot in that sense and how to talk to investors and things like that. So fortunately, things have been going well on that front for our end, but it was a lot of hard work for sure.
Makes sense. I have another question. What advice do you have, just like general key advice you have for like future CEOs?
Yeah, so two things. The first one is it takes a lot of grit, right, and sacrifice. So be prepared to like have very, very low lows and to ride those out until like you can hit those really high highs. And just to put things in context, the story I usually tell is that so the summer of 2017 we'd spent in China to find our motor and our gear manufacturers, right? And so our motors are the brushless DC motors are from China, and we had so it was like me, my 6 month pregnant wife, our 1.5-year-old son, and like 3 of our engineers in a small high rise in Shenzhen, China, right? For like 2.5 months. And then we tried to do an Indiegogo campaign, and we wanted to raise like 150K on this Indiegogo campaign. We ended up raising $7,000, right? So it was like a complete and utter like failure. And by the end of that year, we had like $200 left in our bank account, right? But that month, we found out that we won a Small Business Innovation and Research, or SBIR, grant from the National Science Foundation, which was like worth $225,000, right? Which was more money than we had ever seen before, right? Yeah. The first 5 prototypes that we'd made with $5,000. Like Mark 1 through 5 of the Ability Hand was with $5,000.
That's really good.
So 225,000, right, was like we can actually like start becoming a real business with this amount, right? So in January, like from December 31st, we went from like $200 in our bank account to like the next week we had $200,200 in our bank account, right? And so that's what I mean by like riding these like low lows and then these high highs. And the other thing I would say is like just to be grateful for the opportunity that you have, right? I mean, I'm incredibly grateful, even through all that sacrifice, that I am doing something that I've wanted to do my entire life, right? And that it's having the impact that I've wanted it to have with patients all across the world. So yeah, so being grateful and just having the grit to stick through would be like the biggest piece of advice I would give.
I had a question. How much do you expect PSYONIC to branch out in the future? Like, as far as like maybe, I know you talked about the ability leg you wanted to do, but like maybe like a partial hand or like a hand that's not based on a natural hand or something like that.
Well, so we're probably going to stick with like anthropomorphic limbs, particularly because people usually would prefer the hands looking like, at least having the functions of a natural hand, not necessarily like looking like it. They actually prefer the bionic look. That's thanks to like Star Wars and like science fiction and all of that, right? But the cool thing about that, and this is the story I usually give, is that when we went down to Ecuador again in 2018 to work with Juan again, and we brought down like this version of the hand, like the black carbon fiber look, as well as one that matched his skin tone. And we thought that he would prefer the one that would match his skin tone, but he actually preferred the black bionic one, looking one. And so the reason he gave was that he said that when he walks down the street, he feels like RoboCop. And the thing is that when it tries to emulate like the look of a natural human hand, you can still tell, right, that it's not real. And so the default reaction of people are one of pity. It's like, oh, I'm sorry you lost your hand, right? But when you walk down the street with this, right, like someone sees this and they're just like, oh my goodness, that's the coolest thing I've ever seen, right? Like, and it gives the users ownership of that narrative, right? That this isn't something to be pitied, it's something to be celebrated, right? And that was something that was critical for us in making a decision to like with respect to like the look and feel of the hand itself. So that being said, one of the things that we're working on is a partial hand prosthesis, so that directly integrates into your bones and then also sutures onto your tendons as well. And so we have an artificial tendon that runs through the actual mechanical finger and then sutures onto your residual finger, or your residual tendons in your palm and the dorsal side of your hand. And the idea there is that it's a muscle-powered prosthetic, right? There's no electronics involved, but it also gives you what we call proprioception, meaning that you know exactly where your finger is positioned and how much tension you're providing from your muscles, because your muscles are the thing that's controlling it. And that's one of the biggest problems with prosthetics like these, is that you can move it around, but you have no idea like where the fingers are located unless you're looking at it, right? So to give the users that sensation back, that proprioceptive sensation back, would be really huge. And so where I see this feature heading is towards this biological integration, right, between like the electromechanical devices and like the human biology itself, right, where we're like connecting it to your muscles directly, connecting it to your nerves directly, connecting it to your bones directly, and it's going to make a huge difference for the patients.
Yeah, so this is kind of a related question, not really relating to like any of the engineering or like, specifics, but do you think that like in the future, it'll be feasible to make like superhuman appendages that like, I don't know, like just to give an example, like super duper strong legs or something that make you like jump really higher? Or do you think those will be made, and do you think they'll be like what are your thoughts on like that?
Yeah, I definitely think things like that are possible, where you can have like superhuman abilities. I mean, even right now, right? I mean, like things like 360 degrees of wrist rotation, or charging your phone from your arm, or playing music from your hand, right? I mean, those are all like abilities that that natural arms do not have, right? And so I do think that I see a future where devices can head in that direction as well. And I think I mean, it'll be interesting to see what kind of like ethical questions that end up coming up, right? Like especially with like things like the Olympics, right, or the Paralympics, or like I think they have one that's specifically for like bionic limbs now called the Cybathlon, right? And the idea I think at the Cybathlon is like, what can you do that is like superhuman, right? So yeah, I think it's definitely going to happen in the future, and I think it's going to be interesting to see where this technology goes.
I have another question. So how like do you have like any sort of here, let me so what are some like typical problems that you like day-to-day problems that you experience in terms of like being CEO and working on the hand?
I don't think there's anything necessarily typical, because it changes like from day to day to month. Like the things that I'm working on now are like completely different than the things I was working on like a year ago, right? And so like a year ago, I was like much more heavily involved in like the operations, like making sure that the manufacturing is running smoothly and things like that. But now our director of operations has taken over that, and my focus has more shifted over to like sales and marketing type things, right? And so like that's why we've got like these fun videos of me of our patients doing like bottle flip tricks and arm wrestling and things like that, right? And so yeah, it depends on like the time, right? I mean, right now our biggest hurdle, like I said, is like this chip shortage, right? So like that's one of the things that we're trying to sort through and get over. But like by the end of this year, we should be past that, and then it's going to be something else, right? So yeah, so it changes, and I guess that's part of the thing about being a CEO, is that you kind of like you have to adapt, and you have to like fill in all the gaps of like everything that like put out all the fires that are happening at all times that are completely different and unexpected a lot of times.
So would you say that your technical contribution to the hand like the actual bionic hand was a lot higher in the early stages, and it's allow like a lot less.
I mean,
Like
I guess
how,
yeah. So it depends on what aspect, right? So like for example, yeah, like 5 years ago, or like 3 or 4 years ago, even, right? I was doing a lot of the coding, right? I was doing a lot of the embedded systems coding that was on the hand itself, right? And I was working on like some of the electrical circuits and things like that too, right? And I don't do any of that anymore. But for example, like some of this newer stuff with like the machine learning algorithms, I've been like working on developing some of those things for like the newer stuff, right? Or like the artificial tendon stuff, right? Like there was a lot of engineering that went involved in that, and like coming up with the design, and like and so once we got to a point where I could just then like tell my mechanical engineers to like run with it, right? Then I kind of like handed it off to them, right? So there's still a lot of engineering that I'm doing, but it's usually more for the newer stuff, and to get it to a point where then I can like hand that off to our engineers on the team.
yeah.
All
right,
I have a question. Or
Oh, sorry.
I'll just go. Like, I don't know, like for a prosthetic hand, I'm always interested in how precise they can be, because I know that like the hand itself has a ton of joints and bones and tendons. So like that's all to make it precise in its movements. So like you have, like, I'm not talking about the pre-programmed gestures, but in terms of the future. So like sure, you can have a electrical signal which says to move, I don't know, this finger this much, but how can you actually get that degree of preciseness with your motors and like engineering?
So sorry, I'm trying to think of the best way to answer this question. So I mean, the motors itself are like ridiculously precise, right? So that's why I like the hand itself can be as precise as we need it to be. But I think what you're trying to get at is like, how do you go from like the noisiness of like the nerve signals to like the precision of that you need for like the motors in the hand. And I think that will all come down to like the fidelity of the data that we get, like the rich, like how much data we get from like your nerves directly, as well as the quality of the algorithm that we can use, right? And so we're looking at TensorFlow in particular as the machine learning algorithm. And so that's if you guys are familiar, it's like one of the deep learning methods, and that's what we use to do like the that webcam demo as well. And I mean, in just the last 5 years, TensorFlow has come like such a long way in the computer vision front, and just like handling that kind of data. And so, I mean, to be completely honest, is that we don't know because we haven't done it yet, and that's the whole point of research, is to figure out how we can do it. But if I were to make an educated guess based off the evidence that I've seen like lately, is that with algorithms like TensorFlow, and if we get a rich enough data set, we should be able to get that precise level of control that we want on the fingers.
I have a question.
Mhm.
So is it a concern of yours that someone with this hand, like, how are you going to make it so that the amount of force it's applying is like appropriate for the situation? Because I can just imagine, like, you don't want the same amount of grip like you would like holding a chainsaw as shaking someone's hand. So how is that a concern of yours, that you're like it's going to be too like hard to tune that in?
Yeah, so one of the things about our fingers is that we made them compliant, so you can see that they have like this flexibility to them. So when you grip around an object, it actually like takes the shape of that object in particular. So it doesn't necessarily like hurt or crush like things, right? But one of the things that so the user has control over what their grip force is, right? Based on how much they like flex their muscles, right? But one of the things that we employed is something called a contact reflex. So because we have the touch sensors in here, when the touch sensors detect like a certain amount of pressure over a threshold, what we can do is we can automatically slow down the motors or stop them entirely based on like the touch sensing, right? So that way you can grasp that hollow eggshell without cracking it, because the touch sensors detected touched an object and stopped your hand from crushing it any further. And then you can like really squeeze on it if you wanted to, and like really dial in that force. So that's one of the ways we do it. I mean, that being said, like we've shook like I don't know, like over like 1,000 hands at this point, probably with this with our bionic hands, and like they've been fine for like shaking people's hands without crushing them. So
Yeah, I have a question. So I can imagine there's like a lot of data being sent from like the sensors to like the microcontroller. So has there been any problems in the past iterations of the hand where maybe like the microcontroller is heating up, and do you have any like cooling mechanisms?
We haven't had any issues with the microcontrollers heating up. We more so would have issues with the motors heating up because we're running them at like very high currents. So yeah, the hand does get warm after like using the fingers for a while. But the problem is that we need to waterproof seal it as well. So we can't like put vents in there, fans in there, or anything like that. So the hand runs warm sometimes, but it doesn't really like melt down or anything like that.
Okay, that makes sense.
You were talking back then about like your ups and downs, right? What was your biggest down in like terms of hardware and your engineering, and how did you overcome that?
I mean, I guess one of the biggest downs recently was the lack of finding a chip, like the chip that we were using, which was like an STM32F3 or F301 or something like that. And then like having to redesign like the entire electronics board based on like a more ubiquitous chip that was interestingly, it was less powerful, but it forced us to write the code way more efficiently. And the silver lining was that by writing the code much more efficiently, our clock speeds are like loops are running like 10 to 100 times faster than they were before, and it improved like our torque control on the hand because it's running so much more efficiently as well. So yeah, I mean that's like one example. I mean on like the mechanical side of things, like I think we like 4 summers ago when we were trying to make these flexible fingers, we used to just make them completely out of like a thermoplastic polyurethane material. It's basically like rubber. But the problem with that was that if you held something heavy, it would just like kind of slip out. So we needed to like stiffen it with like a rigid material that was stiff in certain areas. And so we used nylon to reinforce those areas. But like we have a bucket just full of like hundreds of iterations of bones that like failed like our like 350,000 cycle test, and like just like all these different design iterations that just didn't work until we found the one that like could actually last 350,000 cycles. I think it's lasted like 750,000 cycles of just like flexing back and forth that design. So this, I mean, it all just goes back to like, having grit, like, and having the foresight to know that you can come to the other end of it. You just need to fail fast and iterate quickly.
I have a question. What language do you use to control the hand?
Everything is in C.
Okay, that's what I was thinking, because low level and stuff.
Yep. Yeah. Yep. Everything is in C. I mean, I guess like that webcam demo, like the software was written in, that was in Python. But then our phone app is written in, what do you call it? React Native, so JavaScript. But everything on the hand is all C.
And you do that just to make it as fast as possible?
Yep, exactly. And as memory efficient as possible. And we need direct access to like the memory registers, which you can't do with like a higher level language like Python or Java. You're very resource limited in these settings, right? So like there's a very small amount of memory compared to like your computer. There's the processing speeds are a lot slower than like the processors that you'd find in your computer as well. So we need to make sure that that's as optimal as possible when we're running like sophisticated algorithms on the hand itself.
Have you had any challenges using C other than, I guess, just it taking longer because C is hard to code in?
I mean, we're used to it. So
Okay.
the more practice you have, it doesn't get it's not that hard.
All right. Thank you.
I have a question. Are you guys accepting high schoolers for intern positions? Because I'm sure a lot of us here would be interested in a position like that.
Potentially in the future, not yet for this summer. And like I said, we're in the middle of a move, so depending on where we end up moving to, then we can reassess at that point. But yeah, keep in touch. You guys know how to contact me. You got my contact info. And then yeah, and especially if we end up moving to San Diego and you guys take a trip down from Davis to the SoCal area, we'd love to show you around and you can see the hand in person.
Yeah, that'll be awesome. Cool. Well, we have reached past our scheduled time, so don't want to take up too much more of your time, Aadeel. And we can conclude the meeting if no one has any more final questions that they want to get in before the end.
Cool. Well, thanks for having me, guys.
Yeah.
Well, yeah, thank you so much, Aadeel. We really appreciate it, like everything that you've just talked to us about, and I'm sure we all learned a lot.
Awesome. And if you guys have any other follow-up questions, yeah, feel free to email me. Like I said, you guys know how to reach me.
All right. Thank you so much.
Yeah, thank you.
Take care.
Thank you.
Thank you.
Thanks so much, Aadeel.